And my name is Teja. And in this video, we're going to look at the notion of Eigen Decomposition, which includes, of course, eigenvalues and eigenvectors. Eigenvalues and eigenvectors. Okay, so these are some vectors, and there are some numbers, and these are special. That's what it means. So why are we learning eigenvalues and eigenvectors? They are a nice application of change of basis and are related to words that you might have heard of, including singular value decomposition, and principal component analysis. Okay, these are some really nice tools to use if you want to do what is called dimensionality reduction. And all this means is that, for example, maybe you have some data set which has maybe 100 features, and somehow you don't like working with 100 features, or you think that there's a less number of features which actually can, tell me, can predict some outcome. Then maybe you want to create some new features. You can, of course, prune the first set of 100 features and get some smaller number of features, but you can also create some new features by which hopefully are smaller. Also, and we can achieve this by doing some sort of change of basis. Okay. If the number is smaller, right? If the number is smaller, then essentially we have achieved what is called dimensionality reduction. We have reduced the dimension from 100 features to maybe 10 features. Okay. First of all, and the new features are, these features need not be the same as the original features. So we have essentially changed the basis. For example, in the original basis, some representation like age, education, and so on, right? Maybe hundreds, 100 such numbers. In the new features, maybe there's some combination of these guys, which are, because we changed the basis. Okay, there will be a different representation. So what is the idea of eigenvalues and eigenvectors? Linear transformation A, and we want to, and the key idea here is that if there is transformation A, it takes an input vector, maybe vector v, and gives me an output vector, maybe u, right? Let's think of there to be an input vector v such that the output vector is actually not u, but maybe 10 times v, or maybe 5 times v, in the sense that the output vector is still in the span of v. Remember, what is the span of v? Let's say in 2 dimensions, if v is this vector, then the span of v is any scaled version of it, maybe positive or negative. Okay, maybe multiply with -1 times v. Maybe this vector is in the span of v. This huge vector, 2 times that, is also in the span of v. Okay, so the question is, given a linear transformation, are there some vectors for which the resulting vector, output vector, maybe these, we need to, of course, have transformations which are from the same dimensionality to the same dimensions. Let's say from 2D to 2D. Does it a given input vector, a specific vector, to a vector on the span of the original input vector? Okay, maybe there are some vectors like that, maybe there are none, right? So for example, so let me quickly give an example. Let's say A is A00 D. Okay, this is, so is there a vector for which this vector will give back the same vector, but with will give back a vector which is on the span of the original vector, so that we can see. So let's say for us, here you can actually just see that. Let's say there's a vector, okay, then this vector will give me a vector which is so A, right? Yeah, A and D, right? So 1, 1, and it gave me a vector which is, sorry, this is not the vector. Where is the eraser? Yeah. Let me not actually use 1, 1. Let me use 1, 0. then gives me a vector which is a comma 0. So I got 1 comma 0 as the input, and I got a comma 0 as the output. And a comma 0 is just a multiple of 1 comma 0. So the output vector is in the span of the input vector. So this is a special vector, and the scaling of this input vector is the scale is a. So that is also a special number. In fact, these two, this is called the eigen vector of this linear transformation, and this is called the eigenvalue of this linear transformation. Okay. Similarly, there's one more vector which also does the same thing, and I chose this matrix A in a special way to illustrate this. For this, you get a scaled vector which is 0 comma b, which is a scaled version of the input vector. So this is also an eigenvector, and b is an eigenvalue. So a and b are the eigenvalues, and 1 comma 0 and 0 comma 1. This is for a special matrix A, which had only diagonal entries being non-zero. So right, so we found two eigenvectors and two eigenvalues for the special matrix. But in general, for a transformation, also there will be some eigenvectors and some eigenvalues. So in general, what are these? So it should if I input the vector, this v is an eigenvector. If I transform that vector, I get a scalar multiple times that vector itself. So some elongated or shrunk version of that vector. Multiple can be positive or negative. Okay. So it could be or 3 or 1 whatever 1.1. So okay, so at this point you can ask, okay, do all linear transformations have eigenvectors and eigenvalues? And for example, in this case, I had A being in 2 dimensions, right? 2-dimensional input, 2D to 2D. It had 2 eigenvalues and vectors, 2 representative eigenvectors. I call them representative because it's not just 0 comma 1 is an eigenvector, 0 comma b is also an eigenvector, because 0, if I input for a 0 comma b vector, if I transform another matrix, for example, right? So 0 comma b square is in the span of 0 comma b. Okay, so these are not, I would say, what are called unique, in the sense every vector in the span of for example, the vector 0 comma 1 is also an eigenvector. So let's not worry which from 1 itself. Okay, so this transformation has this particular values into eigenvectors, but there are transformations which may not have real eigenvalues. Okay, in the sense that they may not have a vector on which they can act on and give back a scale version of that vector. Okay, there may not be any such vector, right? That's possible. And it's also possible that they may have too many eigenvectors. Okay. In the sense that I just wanted to point out that the number of eigenvalues and number of eigenvectors can need not be tied to the dimensionality of that linear transformation, input dimension or the output dimension. They could vary, but let's only focus on those transformations for which you actually get the number of eigenvalues to be exactly the dimension, and therefore we have the same number of eigenvectors as well. Okay. So if we have the same, so if the same eigenvalues, I should say the same number in my writing, and that's showing up, but if we have the same number of eigenvalues as the dimension, then we can do a change of basis. So what are we going to do? We had, let's say our vector representation was the original basis, let's say A, B, and C, right? I know how to change basis from here, right? I know if I can use the eigenvectors that I know corresponding to eigenvalues, let's say those are v1, v2, and v3. Then I know that in the changed basis, if I have a representation x, y, and z, then I know how to go back to the standard basis, right? So this is the change of basis matrix, and let's say I can change the basis. It turns out that also note that it turns out that these eigenvectors are perpendicular. What do I mean by that? Are perpendicular to each other. Okay, something like this, where there's an angle between of it, the vector are perpendicular to each other if their dot product. Remember the dot product. So v1, let's say the v1 is the first eigenvector. Dot product v2 is 0. Okay, so that's what it means to be for two vectors be perpendicular. It just means that they are aligned in for example, two-dimensional space. The angle between them is 90 degrees. Okay. So if we do a change of basis, actually let me do the correct basis change. So let's say if I do the change of basis from the original space to the new space. So remember, what I have is a linear transformation A. I computed its eigenvectors and I stacked them together next to each other, and created this change of basis vector. Let's call it vectors, change of basis matrix C. So let's say this is called the C matrix. I want to have the basis elements to be v1, v2, and v3. So that would be my change of basis matrix inverse if I'm going from the first system to the second system, which means that xyz is in my original coordinate system and abc is in my eigen coordinate system, right? So let's say, so the basis vectors were generated from my original linear transformation, and I'm just calling that the change of basis matrix as C, C, and then of course the inverse transformation as C inverse. So I can do this, and the benefit of doing this transformation is as follows. So let's say so I have the A, B, and C as the representation. This vector over here is a representation of x, y, and z in the second coordinate system, which is the eigen coordinate system in the eigen basis basically. A, B, and C is a representation. So it turns out because A has the property that if v1 if it gets multiplied by v1, which is the basis in the second coordinate system, that is the same as getting v1 scaled, right? So in the second coordinate system, okay, so let me rephrase it this way. So if I want to, let's say I have vector x, y, and z, and I want to apply a transformation A to get a vector, u, v, and w. Okay, this is in the first system, right? So I have the linear transformation. I have a vector. I want to find its transform. Maybe I also want to find its transform and apply A twice, or maybe A thrice. Okay, let's take this example. I want to apply A thrice in the first system and get a transform vector u, v, and w. So a way to eigenbasis is now going to be useful because I know how to go from, let's say I compute the eigenvectors of A. Let's say there's a v1, v2, and v3 that we show above. I can apply that C inverse transformation that I wrote above to get intermediate representation A, B, and C. And here I'm going to apply a particular transformation, which is going to be applying D, which is going to be a specific matrix. And this is called a diagonal matrix with the eigenvalues on the diagonals. So the lambda 1, lambda 2, and lambda 3 corresponding to v1 and v2, v1, v2, and v3. And sorry. and zeros here. So this is a 3 cross 3 matrix. So I can apply D thrice. Okay, and applying D thrice is the same as saying D times D times D. Turns out to be this is just equal to lambda 1 cube, lambda 2 cube, and lambda 3 cube, 0, 0, 0, 0, and 0, and 0. Okay, so applying D thrice is just multiplying the lambdas, and in fact multiplying D with a vector such as A, B, and C is equal to lambda 1 times A, lambda 2 times B, lambda 3 times C. Okay, it's just multiplying the representation. So so if I want to apply transformation A thrice, I can compute its eigenvectors, get the eigen basis, and so I know the transforms to change the basis, C inverse to get to the second system, and I can compute the transform, maybe it's D, E, and F, and then apply the inverse transformation and go back to the original system by applying that transformation change of basis matrix C. Okay, so this is what I can do, and this just makes the computation easier. Remember, multiplying matrices with lots of entries everywhere is going to be quite cumbersome computationally. Okay, let's just wrap it up with some connection to machine learning. So let's come back to this principal component analysis. The objective is to go from, let's say, 100 features to maybe 10 new features. Okay, and the way you do it is essentially by change of basis. Okay, so you somehow so you want to go from 100 features to 10 new features. So the way you do it is work with a transformation. So you you think of a linear transformation, okay, which it turns out to be is the covariance matrix, but that's not very important. So you somehow figure out a transformation, and from that you figure out the eigenvectors, maybe v1 to v10. Okay, and once you know these eigenvectors, then you can actually get the equivalent representations. I mean, you'll get maybe this, this transformation. If there are 100 features, this matrix is going to be 100 cross 100. Okay, because it's, let's say, the covariance matrix. So you actually will have potentially v100 eigenvectors. So what we're going to do is do a change of basis of these 100-dimensional observations into the second basis system, but where it turns out that the diagonal matrix, let's say we order the eigenvalues in terms of decreasing order of magnitude. So let's say there's lambda 1, lambda 2, all the way to lambda 100. What we're going to do is we're going to just retain, we'll have an equivalent, in the second system, we'll have an equivalent vector, right? For every vector, maybe there's there's an original observation vector with age, income, education, income, and so on. Maybe I got 100 numbers here in the second system, right? So what I'm going to do is I'm going to chop off the 90 of the coordinates and retain the top 10 coordinates, where top 10 just means that the corresponds to those coordinates because my diagonal matrix, I just ensured that the eigenvalues are ordered according to the decreasing magnitude. So this is the highest magnitude eigenvalue, and so on. So this is a way to just think of why change of basis, and in the changed basis you can kind of remove some coordinates basically of your new feature vectors, and in fact the effect is just this. So think of the original data points as like lying in as being like this. Maybe these are points over here. So instead of representing each feature as a two-dimensional, with two coordinates, with maybe age and income, what you're going to do is you're going to change basis. So this is going to be the new basis. In fact, this is going to be the choice of your eigen basis. It turns out because of appropriate choice of the appropriate choice of the linear transformation. And then here you can see that in the second coordinate, the magnitudes of, if you represent points in this new basis, the second coordinate, this coordinate, does not have any magnitude. So you can just represent the data points using a single coordinate. And in fact, this basis vector is the eigenvector corresponding to the highest I guess eigenvalue, and so the single numbers are enough to represent your data in this new changed basis, okay, which is the eigenbasis. So you have effectively reduced the dimension. Okay. This was a very quick connection to PCA. I would urge you guys to now go back to some of the topics that you've seen in business analytics and machine learning, and connect the dots with respect to the topics that we've seen in this video series. That's all for this video. Thank you.